for the intro. I suppose as a John student, I'm the next best thing. This project I'm going to talk about today has been co-supervised also by Professor Tara Hutchinson. So I just want to thank them for their guidance in my work on this. It's titled Ground Improvement-Based Protection of Transportation Infrastructure in a Performance-Based Earthquake Engineering Framework. And I included the full title here, Centrifuge and Numerical Modeling. Today, I'm going to focus exclusively on centrifuge testing, which has been the bulk of my focus over the last year. So outlining my talk today, I'll introduce the concept of a rocking footing and the design philosophy behind it. You're going to have to trust us soil engineers on this one. And then I'll go into my test methods in the centrifuge at UCSD, the scope of my tests, the two different improvement techniques I used, sand cement mixed columns, as well as a scaled for the centrifuge, 3D printed geogrid, and some of the ground motions I used. And then right into test results. And I'm going to welcome feedback in that. I think that's been a big theme today, is making the work we're all doing here accessible to practitioners, accessible via tools and databases. I wish I clicked onto that at some point. Okay, there we go. So the concept of rocking footings. They provide energy dissipation when you mobilize the soil capacity. They tend to recenter themselves during shaking. They feel the pull of gravity, moving them back to center. And they move damage away from structural components, where these loads can be concentrated if you have a more traditionally designed stiff footing. However, there's some trade-offs with this. You can have compatibility issues. There is some uncertainty in how much that footing is going to move when you allow it to uplift and rock. A common problem is too much settlement. So we'll look closely at that today and how ground improvement can prevent those issues. So here's a nice schematic from paper by Tsatsis and Anastasopoulos. They also did centrifuge testing of rocking footings. They actually compacted a crust layer near the bottom of the footing. The conventional design on the left there, you see the damage is concentrated in the column. You're getting hinging there. And that can be problematic. You know, and if you can share this ductility demand with the soil, you see on the right, make the footing a bit smaller, reduce that factor of safety of bearing a certain amount, you'll mobilize rotation, settlement, energy dissipation in the soil and share that demand more evenly. So here you see a schematic of my model scale footing in the centrifuge. The bridge deck is just represented by a lumped mass there. I ended up doing 2 test series. You'll see that there were some nice comparisons of repeatability of the results between the two. I did similar ground improvement techniques for each. A heavily loaded footing and a very heavily loaded footing. And you see in the literature that instead of factor of safety for bearing capacity, you see instead critical area ratio, this A over AC. You can almost think of them as the same thing. But the critical area ratio considers the bearing area that's supporting the footing as it rocks on its side. And so it has a little bit different shape factors. But you see, I've got a medium dense sand layer, the footing there. You'll see various configurations of cement mixed columns and geogrids. But before I get to that, I want to introduce the motions that I used. So this is following general guidance from FEMA 461 for shake table testing. I would do a series of white noise shakes to characterize the rocking natural frequency of my structure. And especially that's capturing SSI effects, of course. And then I would go to sine sweeps, where this amplitude peaks at that rocking frequency I determined from the white noise shapes. And you can see it gets a couple of cycles that peak at that natural frequency and causes all the damage. And then at the end of the test, I hit it with a really demanding harmonic. It's really coaxing out differences in the improvement techniques for a very demanding event. So here's the first series. You're going to see graphs grouped, as you see here, when I get to the performance metrics. So you see, I've got the white noise there starting off, characterizing things. I actually have a series of tests with no ground improvement using the harmonic and the sine sweep motion. I wanted to really coax out the case without ground improvement, because that's the basis of the comparison with ground improvement. And then you'll see I went through a series here with paired columns, long and short, central columns beneath the footing, long and short, and then paired columns, but with the interface of sand between the top of the column and the bottom of the footing. This came out of discussions we had with practicing engineers, Jim Gingery, Li Sheng Xiao. They suggested that crushing of the columns could be a concern, as that rocking footing kind of pounds the top of the columns. And so these are all for the heavily loaded footing. And you'll see some repeats here now for the very heavily loaded footing. Paired columns, a long central column, and then the 2 geogrid tests. So brief overview of how I mixed these columns. They were mixed according to the FHWA mixing manual, placed in situ after they were cast. I was in the mixing manual following other procedures. I found that at a more common water content to binder ratio of 2.5, I was getting lower strength than I wanted. I ended up using those with the heavier structure in series 1, or rather the lighter structure. And then I went to a lower water content that's kind of at the limit of a ground improvement application, and use that with the more heavily loaded footing. We had 2 visiting undergrad students this summer that really spearheaded the geogrid angle on this project. It wasn't something I originally planned, but they really took it by the reins. They were able to print 2 different materials. They thought about scaling in terms of the sand grain size. You see the printer up there on the right. We did some tensile testing. What we saw is you can really scale the aerial dimensions of these just fine for centrifuge use, but the thickness is a limiter. It's hard to get them that thin, scaled down to size. We did have some researchers, Zinska and Bolt, that managed to print very thin geogrids. You see their data compared to a commercial product tested by Stathis here. And the 2 products that we printed, we had one that was much stiffer and stronger. But then once we saw that, we chose a much more flexible material. This green curve is TPU material, and we were able to get closer to the commercial products. So we ended up with 2 materials that sort of spanned what you would see in a typical product used in the field. So my test procedure, incorporating everything here, I pluviated through a stack of sieves to disperse the Ottawa F65 sand. It's the same sand they use at Davis nowadays for all their centrifuge tests. I ended up with about a 50% relative density deposit. And then to place these columns and the footing in as close to an at-rest pressure condition as I could, I'd spray WD-40 around the footing area and just get a light cohesion. This is similar to techniques used by other groups as well. And I just want to emphasize there's no structural connection between the columns and the footing. The key here is allowing it to uplift and rock. So typical kinematics I'd observe during a rocking test. This is going to inform, this is the basis of all the metrics I'll show. I'm comparing on the left here a test without any ground improvement and a test on the right with long paired columns. And I've got lines delineating initial rocking stiffness and moment capacity. So those provide a reference here to compare between the two. I would see that with the paired columns, they maintain the rocking stiffness longer, and they experience much less settlement even as the moment reaches its rocking moment capacity. And I found that the settlement was only about 1/3 that of test 4 without ground improvement, given an identical shape sequence. And I want to introduce this concept of a recentering ratio that you'll see shortly, as long as we got this settlement rotation graph handy. The recentering ratio is a function of the return to center, theta res there, you see when it's unloaded, how close it returns to zero rotation or upright compared to the maximum rotation it sustained during the shake sequence. So first metric, settlement curves. I found that my baseline cases without ground improvement matched the literature. You see a compilation of tests there by Dang and the thick black line and my black lines for no ground improvement. You see that the longer paired columns, that is the light green line, really reduce settlement effectively over all other cases, except for the longer central column in the light blue there. And I'll just flash forward. I've got the 2 geogrid tests here. You do see that the stiffer geogrid in the pink reduced settlement more than the flexible one. So you could surmise it took on more tension load, more reinforcement. But that central column test I mentioned, it exhibited poor recentering. You see this recentering ratio here against the cumulative rotation demand throughout the shake sequence. The recentering drops off quite precipitously, even at low-level shakes. And what I envisage that as is that it's like an inverted pendulum. It's anchored about that central column, and then all the yielding gets concentrated to one side as it rocks. And so these paired columns are providing a more stable configuration. And you even see differences in the trends as you get to higher and higher cumulative rotations. By taking it to a high demand, you can see differences there. And these long paired columns continue to recenter well at high demand. Finally, I just want to introduce this correlation diagram. It's a way of getting at multiple metrics at once, I would say. In this case, recentering and energy dissipation. Now, whereas the recentering ratio I just showed was based on how it returns to center after the shake is over, this one is looking at the hysteretic load loops. In my case, I'm looking at moment and rotation of the footing. And so, yeah, these ratios are based on the shape of the loading, unloading, reloading cycle. And so in the context of this diagram, if you fall in the bottom right quadrant here of recentering ratio versus energy dissipation, you're said to be in a recentering prone regime. If you're at 1, 0, you've got a linear elastic material. And what you see is all of the load cycles for these tests, for these rocking footings, are within that quadrant. And inevitably, if you do get energy dissipation increasing, you tend to lose recentering. That's kind of inevitable. And there's a zoomed in view. I wanted to highlight 2 load cycles to kind of show you what's going on with these trends. You'll see that this paired configuration, you get a nice pinching of the load loop when it's unloaded. And so that's a very beneficial characteristic of good recentering while maintaining energy dissipation. Compare that to a central column, which is actively tipping over. It's more almost like ovular. It's not pinching and recentering very well. So I've generated a lot of data with these tests. I've got about 20 centrifuge tests. I've just started putting together well, I shouldn't say just started putting together. I've been working hard on our peer draft report, and I got a lot of this in there, much more than what I showed today. But further things I'm looking at is tracking degradation and stiffness. There's a nice paper that just came out that shows dimensionless quantities. They drew heavily on the peer database, the rocking database of tests to produce these plots. I want to add mine to those. I think we could develop characteristic moment rotation curves for designers to use based on the different GI configurations. I've reproduced, I think I showed this last year. This is from ASC 41. They have these trilinear moment rotation curves. And I can't help myself. I have a couple additional strategies I'd like to try. I don't want to go too much over here, but we're very nimble at the UCSD centrifuge. I can do all this by myself. Some of the tests that had poor recentering had that interface layer between the column and the footing. And so I think if I could focus more really on that immediately beneath the footing zone, I might see better results. So I've got a couple examples here. And really it would tie my study very well to this other one that I mentioned right at the outset, where they showed that a shallow crust layer really reduces settlement effectively. So that's all I have. My project is near to its end, but I think there's still time to get feedback, think about the best way to publish everything. So with that, thank you all for your time. And that's all I have.